On this channel, I've been testing pretty much every speculative decoding method I can get my hands on, and this week we got Qwen 3.8 27B, which is one of the most interesting new local coding models. It beats everything else in its size and benchmarks. Then, just a few days later, DFlash got major update, the DFlash 2, promising better acceptance than DSpark with much less overhead. But here's something a lot of people don't know. In Llama.cpp, you don't necessarily have to choose just one speculative decoding method. You can combine a drafter like DFlash with ngram speculation and let the Llama.cpp combine those results for you to get as much tokens as possible. So today we are going to test normal decoding, ngram, DFlash 1, 2, and combinations of them to see how fast we can push Qwen 3.8 27B on Llama.cpp, because this is the inference engine most people use on limited hardware. And if you are new here, I'm Łukasz, I'm senior inference engineer, and on this channel I explain new AI inference techniques in simple, intuitive terms, and then benchmark them properly on real hardware. First, let's jump to the video. Here we can see DFlash 2 pushing parallel drafting one step further. Inco AI claims that we have more than 20% more accepted tokens for every verification pass for around 1% added cycle latency. So we'll test that. And as we can see, we have the support for main inference engines like SGLang, VLLM, Llama.cpp, Llama, and OMLX. Now let's start the quick explanation of why it go now so much faster. So DFlash claimed 20% more tokens out of every verification pass for 1% of extra latency, with the output probably unchanged. So we'll check that for Llama.cpp with concurrency 1, because that's what most local users will use. So the headline demo runs at 70 tokens per second on their laptop. So it's a claim. We don't know what's the measurements exactly, benchmarks, and so on. And if you know from our other tests, you can influence the score quite a bit to make it look good. So the fixed one that they have is the right token was already in the drafter lists, so it was just not picked well enough. So now it will pick it better. Then every drafter slot can finally see the slots before it, because in DFlash, you can check my other videos, we produce all tokens immediately in parallel. So if you produce token 1 and 2, they appear in the same time, so they don't know anything about each other. This will be important, but we'll explain it in much more detail soon. So 2 new parts and 1 unchanged contract. So as I said, we'll now keep the top 16 candidates per position and score the nearby pairs. And 1 coherent path is walkout of scores that were all computed in parallel. So we add a bit of parameters, but it's only 0.6% per cycle. So we'll use the convolution as the backbone. So a 2-tap dynamic convolution will let every draft token position read its predecessor, so the accuracy will stop sliding at the end of the block. Then we still have 1 pass and it's still lossless. So it's supported everywhere. We choose this stem basically because the verification comes from the big model, then it's by theory will not be lossless because the big model make decisions. So basically DFlash 2 will not draft more, it will keep more of what is already drafted. Now let's look how the selection will work. So we have lightweight path selector, we have the speculative decoding, and then we decode is. And this is already verified, so it will go here. Then we have mask, which is 3 draft tokens that we want to get, and the suggestion of these tokens are at position 1, 2, and 3. Then we have, for example, the accepted output that was accepted before in the turn before. Yeah? So the DFlash predicts all 3 predictions in 1 pass, which means that position 1 don't know what's on position 2 don't know what's position 1 and 3. And why it's important? Well, in this case, we have the same tokens in positions 1 and 2, which is not right for any type of sentence that we'll have. So this will mean that if we pick the same word, the verifier will reject the block at position 2 because we can't have this. So we'll lose then all of these draft tokens and compute for nothing. So the interesting part is that the DFlash already keep the 16 candidates in position 1, 2, and 3 already. And in these 16 candidates, there is 99.5% of correct tokens most of the time. But because we didn't know basically what position 1 and 2 are between each other, then we couldn't choose the best one. So we only get like 85% most of the time. So now let's see what DFlash 2 will do. So it don't make a better prediction, it makes better choice from predictions it already had. So it will score every neighbor pair, as we can see here, all of them in the same pass. So 7 times multiplied by 16 times, which give us around 1,700 scores. Actually 792. And it will do it all in one shot. And now what it will give us? Well, we can then walk and we can see what is in front of us, so we can make better choices. So one score is two numbers added together, how much the drafter liked the word on its own, which it already had, plus how well it follows the word before it. So in this case, how well it liked the word here, A, and then the score of itself. And that's how it will work in selector. So we see now that the block survives. The selector only adds the 2 million parameters. Whoops. So as we can see here, we then choose tokens, and we can see that on the output they will get accepted. So we get selected the path. So the block survives, and the selector adds only 2 million parameters and 0.6 to cycle latency. And this increased the accepted length from 4.27 to 4.71. And for this, DSpark needs around 40 times more parameters for much less acceptance. Now, this is the formula that we can see here. So we have the purple one. So this means how much the drafter already liked B on its own. So it had already had this number. So for example, for this, the B will be good. And then we have the full formula, and A, as we can see, the A is the position before. So what will be the rest of the formula? How well B follows A in these contexts, basically. So every line in the grid carried one of these scores. So it's not like token yet. Yeah, it just scores and then tokens. So by doing this, the block survives, and same drafter, same single pass, same lossless rejection sampling get to 4.71 from 4.27. Now let's look how they measure this claim. So they use something that they named recall. And the blue one is how often the token that we choose to draft is actually right. Then we have the green, which is how often the right token was somewhere in its 16 candidates that we described before. So as we see, we start from 85% in the blue case, and we go to 72. But if we consider the 16 tokens, we go from 99 to 87. So as we see, we are better in position 6 than we are in position 0, which is typically the highest because it's straight after decode, so it's easy to know what word would be after. Now, there is something they name oracle. So basically, if we use the green method, we go from acceptance length of 427 to 679. And now, what it tells us, that choosing is cheaper than predicting. Here we have DFlash, DSpark, and then DFlash 2 with path selection. So we add, compared to DFlash to DSpark, 77.8 million parameters, and we add around 9.6% latency. For this, at position 0, we get 4.49 tokens from the base, which is 427. But if we do path selection, so we add only 2 million parameters and 0.6 latency, we get 461, which is much higher than DSpark in this case. So if you watch the other video, you know how it works. There is sequential Makarov head. So basically with 40 fewer parameters and 16 less latency. So if you watch the other video, you can see that the sequential Makarov head, which we explained before, is with 40 times fewer parameters and 60 times less latency loose with the path selection. And we still get the ceiling, which is 679. The number is different because they use different ways to measure it. It depends if you do code, if you do open chat, and so on. Now let's jump to suffix decay. Before I start explaining this graph, two quick definitions because it will be unreadable without them. So we have file here. This is number of layers, and layers are depth, how much computation happens in one pass. There are also positions which are width, so how many tokens came out of it. So separate access a 5-layer drafter and 15-layer drafter can both draft 7 positions. So we have recall 1 here by draft position. So recall 1 is how often the drafter's top guess for a position is literally the same token the target model would have written. So it's basically the correct one. And one more thing before the numbers, because it kills the obvious objection. This measurement already removes compounding. So position 6 number only counts runs where position 0 through 5 all came out right. So a weak tail is not errors piling up, it's drafter running out of capacity, which is something architecture can fix. So here we have the reference drafter, which is in blue. It have 5 layers, like we said, and we see that we start with 85.4% of the time at first position. This is the draft positions. And as we can see, we go lower to around 73%. So quick also note, we start from 16, not from 0 here. And then let's see what will happen if we drop just to 3 layers. So a 3-layer draft starts in almost the same place, but as we see, at the positions will have less accepted tokens basically. Now let's look at another one. So now we can fix it with a depth. So we add 15 layers instead of 5 and 3. And as we can see, the 15-layer drafter holds the tail much better, because as we see, it ends later and the dip is not as steep. But at the first position, we almost gains nothing. So we throw so much more layers, and as we can see, there is a bit of increase, but nothing crazy. So let's look at the cheap version now. We have 2 convolutions per sublayer on the 5-layer drafter. I will show the graph later. So as we see, only 3 layers, and we add 3% of parameters with convolution, and we basically have nearly the same score of the 15 as the 15-layer. So 3% more parameters and 0.7% more latency. So as we see, dev pays for capacity at every position, and convolution solves it where the problem counts, because we don't want to have such dramatic dip here in the later draft positions. We want to have as long draft as possible. So basically the convolution attack the exact problem. Now let's talk about attention. So one cell here is one attention head, and the drafter have 5 layers, and each layer have 32 heads. So the grid holds 160 heads. And this is one head of attention, attention heads, and we have the layers as I described before, and the color is the percent of attention spent inside this block. Now brightness, it's not accuracy, it's each head splits each So each head splits its attention between the context before the block and the position inside the block. So the brightness is the share of that stay inside. So the market one here sends 50.8% of its attention to the draft block and the rest to the context. Yeah. Now let's look at another one. So in first layer, we can see that many heads are bright. So the early layers do the work of linking the draft positions to each other. So the layer 1 average is 30% inside the block. Now layer 5 average is only 8%. Why? Because we add a lot of context here. So by layer 5, almost the full row is dark. These heads now spend their attention on the context instead of draft. So what remains sits in few heads. So a few handful of cells carry early all the within block work in the last two layers. So layer 5 and 6 sits at 76%, and most of these neighbors are under 1%. So nobody designed it, it's training produced it because the context is where attention gains most, and the within block job was left behind. So we give the within block job a separate model and let attention keep the context job. Now, how we do it? That's where the convolution sits. So we have the attention, MLP, this is one drafter layer repeated 5 times, yeah? We add convolution between them. So DFlash 2 inserts these small convolutions around the sublayers. So as we see, sublayer is attention or MLP. And the post places one before and after each attention and MLP sublayer. And the convolution don't replace attention, it just sits around them. Now let's look what inside one convolution. These boxes are not tokens, each box is the hidden state of one position, a long vector of numbers basically. So a real block holds 4 to 16 positions and they are shown here, 1, 2, 3. So now we'll look what's inside one of these boxes. So take one draft position. Will the drafter works? It's not a word. We have here the hidden state. It's a list of numbers, one per channel. So we have a few thousand numbers for this one slot. Those numbers then pass through the drafter layers that are purple. Every layer changes the number. They are still numbers at the end of the stack. So nothing here has committed to a word yet. Now the LM head is the part that leaves the number behind. It turns them into a score for every token in the vocabulary. So we have 100,000 or so scores for one position. As we can see here, we have good, simple, clean, and the scores for it. The scores are illustrative, of course. And then now we choose a word, and that's when we accept it. Yeah. So the drafter takes the top scoring token, and this possession finally will be accepted. So we put good into it. And everything before this point was reversible. So it's not like a commitment yet. Yeah. And this convolution sits in the middle on the numbers. So blending numbers is a multiply and an add. So blending words would mean picking a word first, and that forces the position into a queue. So the convolution works here on numbers, and then it becomes word only here. So each output position starts from its own input vector scaled by k0. K0 is like itself, and nothing is lost. So nothing is lost from the position itself. We can see the formula here, yeah, and so on. Now, then it adds a vector of the position before it, scaled by k1. K1 is the information from predecessor. And position 2 here now carries a trace of position 1, yeah? This is the link that attention gave up in the later layers. So position 1 here has no predecessor inside the block, so it reads the last verified token. That's a real token, not a guess. So this block is like anchored to the text that the target model already produced. Before, in other explanations, people also use anchor, yeah, the first decode token from where the draft starts, basically. And every arrow starts in the input row, so no position reads another position output. So all of them compute at the same time, yeah? That's why we have this position 1 multiple times, because we don't want to do the connection like between them, because they all are computed in the same time. Like all of this, poof, is computed once. But because we use the trick and we do then this, then it's not sequential like in DSpark. So it's one fuse operation. Now the two weights are not fixed. Each one is learned based on kernel plus a small correction computed from the current hidden state. This is what dynamic means here. The mix changes with the content instead of applying one fixed rule. And then the convolution keeps no state between draft cycles and never reads outside the block. So attention, the LLM head and the verifier stays unchanged. It drops into an existing DFlash drafter without touching verification, so the output stays probably the same. A kernel that reaches one position back recovers most of what 10 extra layer buys. So we added 16.5 million added parameters, which is 3%. We added 0.7 added cycle latency, and within block attention layer 4 and 5s, it will fall from 9.4 to 0.5. So by doing these two fixes together, we add basically 1.05 tokens over the DFlash one. So here we have various data sets: GSM 8K, MAF 500, Human Eval, MVPP, empty bench, and we can see here min. So the MTP was the beginning of the speculative decoding with Eagle 3 and so on. The min was around 4.54, so this was the drafter tokens. Yeah. Acceptance, and then with DFlash we have 492, with DSpark 499, and with DFlash 2 we have 597. So it's like evolution. So we have plus 21% min acceptance length over DFlash and 0.48 over DSpark. We only added 1% of the latency, as I said many times before. And the acceptance held for the last position up to 86% on MAF 500. Yeah. So because it depends on the task. Now there are two drafters out today with this method: the Qwen 3.8 27 billion and Muse Glimmer 30 billion. So you can see the scores here. And as we see, the Muse Glimmer performs better with this method, which is quite interesting. And more than a full token ahead of a community DSpark drafter on both models. Yeah. So this is DFlash 1, DSpark, DFlash 2. Here we have MTP compared to DFlash 2. Now you can of course run it tonight, as we said. So this is the copy of the runs, but you can check the basically ones on the website. It will be linked down below. And now let's go to the test. Okay, so now we'll go to the benchmarks that I ran nearly all day for 3-4 days. And first thing first is that DFlash 2 allow only up to 7 draft tokens at the same time, and DFlash 1 in llama.cpp only 15. But this could change because this is pre-PR version. Now, regarding the bench, I use 6000 Pro Blackwell and 96 GB of RAM. This is the llama.cpp version, all in concurrency 1 without reasonings, because some benchmarks basically don't work with it. And also it makes it super long because Qwen like to overthink, and then we need to go into reasoning, and then there is like a lot of talks which reasoning is best, and it seems that most people use medium, but it changes also depending on which quant you use. So yeah, basically we turn it off. Okay, so while I was finishing editing this video at 2 a.m., there is new update on artificial analysis for intelligence of this model. So actually, with the X-High, you can run this model locally, and it will perform as good as DeepSeek V4 Pro nearly, and GPT 5.6, which is crazy for local model. You can run it on one GPU like 590. And also medium and low, so probably you would want to go with medium or X-High. But this is for the artificial analysis. But Agentic index is actually better. Why? Because you do coding. This is like typical model for coding. I mean, it's also good for all other stuff because thanks to distillation. But what we can see here is that this local model that you run at your PC is actually 7th from the top from all the models measured here, which is crazy. So yeah, so X high is 51 and medium is 50. So honestly, looking at these two, and knowing Qwen that it likes to think a lot, I would use probably medium and start with medium and then go higher. So I know I saw there is like 20 videos about which thing you should use, but yeah, it gets answered probably here. And I don't watch these videos, but probably medium is the answer. Looking at these scores and knowing the architecture of these models. So yeah, now back to video. And we use greedy sampling to have as reproducible result. The only difference is if we do like a lot of coding agentic task, then I prefer to use the parameters that are suggested for coding because that makes sense. Yeah. The quantizations for Qwen 3.8 and the one I ran before are not the same. Why? Because we are not allowed to have the exact same version there for everything. But if whatever it was possible, we use it. So for example, for the drafter, we have Q4KM, target model also Q4KM, and so on. The MTP model is Q8 GGF. Why? Because in drafter 1 in DFlash, we use also this, even though there was Q4KM, because at that point there was not this exact version of the drafter. And usually you would not want drafter in lower version because, as accurate it is, you want it to be as accurate basically to get as many draft tokens so your target model will accept it. But yeah, that's a small digression. Now, what benchmarks we will run? So the first one was LiveCodeBench because it's competitive programming problems. All of them are like in the coding space, but they are also like separate problems. So we'll not have a context a lot. So this is like if you will ask a lot of questions of different topics basically. And it's blind to, but there is issue with it, yeah, because like if you work on some code, you do multi-turn coding, so this will not be good measure for it. So I make multi-coding benchmark myself, and basically it create Gradio app that wants to kind of imitate the Llama.cpp frontend. You can check it in the repo if you want. You can run it yourself and everything. Like always, everything will be in GitHub. But basically, I wanted to like simulate specific multi-coding behavior because that would be most closest to like coding on one repo or agentic coding. And this is what these methods benefits also most nearly. Okay, maybe for math it's a bit more, but yeah, you understand the topic. Then the synthetic benchmark, just to trust it for shape because you can't control the exact output input on each of these benchmarks basically that were before. So this is just to check. And then one request to send every sweep is just to write a fresh prose. So write a very long story for the model to basically generate a lot of code. So this is the opposite from code. Yeah, we want to invent fiction and so on. And we use it to check the accepted percentage in this report. So this is example what the synthetic harness will actually send. And there is also issue sometimes that happens here that inflates the benchmark, that basically it uses fictional stories, but if they end, the package goes into kind of berserk mode and just multiply the sentence multiple times. Yeah, that's happened, but this is the best we have. Also, to keep the numbers honest, I was monitoring the GPU temperature, if it's not thermal throttling, and so on. We do one server at a time. Nothing was running on the PC at this point. We have fresh container per each test. We cool the GPU between measurements because this also influence everything. And we try to measure the noise basically to not trust like the scores exactly. So whenever it was possible, we tested or we ran 2 or 3 tests of the similar runs to check the spread, basically. But yeah, I needed to be selective about it, because otherwise it will take weeks. And I measure it, so I can see that the heat is real, but it wasn't as harmless. Now the first thing we'll look is the LiveCodeBench. So I use 100 problems. We replay it in the same order, each allowed to stop naturally, because it decides how many tokens it will basically output. So the number is what matters. We can see all the parameters. And now let's look. So the baseline, Qwen 3.8 without speculation, 67 tokens. We can see inter-token latency, the wall clock, and the output. The output will be a bit different here, because it depends on the model and so on. Then the DFlash, so as we see, it's 2 times 26 times more. And the interesting part, so this is all the Qwen model, because when DFlash 1 was, there was no Qwen 3.8 basically. And we use the best number of heads, and it still is slower. We see it's just 2 times more. So this is basically proving that DFlash 2 is upgrade. Yeah. And then I also use ngram. So ngram, it's a method that I explained in my other video that you can check, which is other speculative method. And it's the interesting part is that if you use llamacpp, you can also turn on these methods, and then whenever possible or efficient, it will be used. So we can see that the speed line against the model was there. And also, and then actually we do a bit of twist. So I explain all the benchmarks we run. So I ran them with just DFlash 2, and then I appended ngram mode, ngram map K4V, because there are different methods. So to do same weights, same GPUs, and just tune these things. And now we can look here. So we have first, the blue is DFlash alone, and then I don't know what is this color, is both drafters, because if you use both, then it will use the one that is better, basically. So we get 182 tokens on editing code with a model. So there is 18 turn session, but for this I only used turn from 1 to 9. Why? Because after 9 turn, I ask it to check the full database and so on, which inflate the score. So I wanted to see it in the not best case, but the worst case, basically. And as we see, we get 35% increase in tokens per seconds after adding the lookup drafters. Then we have some forced synthetic, just few runs to see. And actually we get 52%. So this I will not trust, honestly, because these synthetic generators typically do something dumb, like multiplying the same sentences and so on, and then it don't work. And that's probably what happens, because we can see that in LiveCodeBench, which is the real benchmark of multiple runs, it's only 1%. And then when we do writing a fresh story, we get minus 30, which is interesting, because technically ngram don't use that much resources, but because we were doing something novel, then I guess that the drafters are not benefiting so much from it. And then because we have these two modes, maybe they were being used when the DFlash will be more beneficial and so on, because there's algorithm to choose it. But yeah, it's new thing, it's PR, so it could not work. Now the interesting part is that DFlash is hard capped at draft tokens, and as I said, and DFlash 1 is at 15. So comparing them at their own maximum measures the cap, not the drafters. So DFlash 1 was rerun at 7 on the same binary, and both were put through the same 100 real prompts again And as we can see here, then the DFlash 2 win, which is good. So it's 1.14% ahead. And as we see, the accepted tokens are much higher. So this is something we would expect. And the also interesting part is that the VRAM cost is much lower than DFlash 1. But remember, I used the high quant there also, yeah? And I think it's mentioned here. Yeah, it's mentioned here. So, yeah, this is something interesting that I put in my other benchmarks, but this is like perfect case. So it show us good numbers I explained before because the synthetic drafters like to break. So I ran multiple runs at different context size just to see if how the drafters will behave as the context grows. And here we have it. So we can start from the base, so no speculation. As we can see at maximum context, pretty straight line. The median decode in seconds is 59. Then we have MTP, we increase to 150. Then the blue is DFlash 2 with N7. So this is maximum. So this is actually hard to. So it's yeah. So it's 211, and then DFlash 1 with N7 is actually more to which is 219. But these scores are like perfect example, which will probably not happen. So trust more the Agentic scores of multi-turn coding, honestly. And then we have the ngram only, and as we see, we have a big boost with ngram, which is basically free, which means that the synthetic benchmarks are still not working, even though I updated package probably and so on. And this we have then the DFlash 1 with 15, so it was the max. But if we use DFlash 2 with ngram, we go over to 500 tokens in this context. Yeah. And we can see these scores here. So with DFlash 2 with lookup of ngrams, we get 8x increase on this context, which will probably increase because the synthetic benchmark can generate as many tokens that are unique in a sense. And this is mentioned here also, yeah, in the report. And there will be more details probably in README if you are curious. So then we would like to find the best amount of draft tokens technically. Yeah, the maximum is 7. We can take it, but there is a bit of cost always involved in it. So what I do is I cut the LiveCodeBench problems to exact number of tokens and then a task instructions appended it. And we do 16 prompts per width. And we run DFlash 2 and MTP with it, just for comparison. And as we can see, we achieve peak for MTP around 4, which actually 3, 4, which this correlates with typical setting through all SGLang VLM cookbooks that you can look for big models, yeah, if you look for high true output. So this is quite okay. And here we get 5, which was also mentioned by the authors of the paper. They suggest sometimes 7 or 5 because, yeah, it depends as always on what you do. But if I would start around 5, yeah. And we can see also there is point when it goes quite down, yeah, because this is all because of the context and so on. In my last test, there was common complaint about speculative decoding and that it fall apart at log context, yeah. And there are a few costs related to it, yeah, because there's prefill, so everything that will feed before we see the token, and then decode so the output. So what I do is the LiveCodeBench problems were concatenated and then trunked to exact token count. So we know that this is exactly 16,000 tokens of coding, not something else. And then we set up it to different context lengths to basically check it. And we can see here where was the point that we start getting the decrease. So this is the log scale of prompt length and share of baseline prefill speed that we keep. Yeah. So look up, typically the cost is minimal, but actually we noticed something. I think this is at 1, so this is the same. And yeah, I was like surprised. And as we see MTP and DFlash, then also with context, actually it's getting there. So I make also this table, which basically tell us about prompt depth, the prefill token per seconds, with no drafter, with DFlash, then the speed that we kept compared to base, and then the prefill time with no drafters, and then prefill time with DFlash. And as we see, it takes more with DFlash. Yeah. So we then have the extra time. But then this extra time could be basically compensated because of decode that takes much more. So then if we calculate it, then to break even, we just need to get output length of this amount of tokens. So basically it looks like it mitigate each other, but this is not the best test you could probably do. But this was the best I came up with the time to basically run it. So as we can see, we have the drafter and the tax that we need to pay at different context lengths and so on. And as we see, the lookup, so the n-gram is cheapest. This is probably some rounding error at this point. So then basically I run again my Agentic coding benchmark, and you can see here we are like setting sliders, server health probe, and so on. And then from turn 10, we will basically ask it to remit file it already wrote, then do like full code investigation, adding dog strings, book reports, and so on, which basically involved feeding into memory all of the code that we already generated. And I ran it then on all 18 turns, which inflated. And as we can see, yeah, they inflated. Actually here, not that much, which makes sense because the n-gram give the biggest boost, yeah, when we feed the full context like a code base that was before, yeah. So this is like quite clearly visible here. That's how I designed this test. So basically we can see that the n-gram will allow you, for example, if you rebase full coding database or something that you have, it's worth to turn it on because it will be faster. Actually, the models in llamacpp turn so fast that you could create flag or something and just rerun it or script and so on, which could be interesting. And then we can see that the lookup only also give quite a boost. So yeah, but you can use all of them together and then you get basically this, which is like 344 tokens per second. And here it's all of this in table. So as we see, 6 times more. The acceptance is oscillating because this I actually don't check. I think I check it on the official version, but I don't know with this new one how it works because the acceptance length could be only for DFlash 2 or for all speculative methods, but it's kind of close. And it also is multi-turn, so there's many things that could go wrong there, so this oscillation is kind of okay. Yeah, the maybe good thing to mention is that you have many parameters that you can specify here, but I use defaults because it's like making grid search along of them and benchmarks will take probably a month. So there is one parameter that I wanted to mention, which is draft-p-min. So this parameter stop drafter add block early when it's unsure to save some resources, basically. Yeah. Of course, in autoaggressive, it will make probably more savings, but I wanted to test it because I saw that like even in the VLM SGLang in DSpark, there is specific parameter that, for example, DeepSeek Lab use. So basically, when you have high true output, high concurrency requests, you want to modulate the number of draft tokens here because it still uses utilization of server. So, for example, if you have not many requests at high concurrency, at some point you can allow more draft heads because you have more resources to spare. But if you will keep the same number of the heads when you start getting 4 times more requests, then this drafter will be actually not helping you, but making all the requests slower for the users. So what they have is they have thing that basically measure all the GPU utilization resources and decide which number you should get. But yeah, I think it was just this week added to VLM. So yeah, I wanted to check if it works here. And there are some issues basically, and we do some control runs and so on. And it seems like for DFlash, the change is not even there. It could be working, but we could not see it because the server did basically identical work for us. And on MTP, the flag works, which could explain because it's longer. So probably, I don't. Depending on the time you watch this video, you can check this parameter because it could save you some resources, or maybe there will be already algorithm that will tune your number of draft tokens by your best based on your resources. And I do quick tests with the draft if it gets shorter and if it survives better. But the true output was like, yeah, I don't see big change, but this will be hard to observe because I have like basically too big GPU to observe the big saving here. I will need to run, like I said, high concurrency probably workload to see it better. So yeah, there are some limitations, yeah. So I want to be clear about it. There is no deep context decode measurements anywhere in this study. Why? Because I don't have time. And the multi-turn harness can, of course, measure wrong things because if you can use repetitive things there, yeah. So it's always best to check. And yeah, for good measurements, you should rerun everything and so on, but it's not always possible. I rerun it a few times. It's sometimes mentioned, sometimes not, but basically you should run the benchmark again the next day to prove all the scores if there is no errors and so on. And the no quality measures were taken because we tested it on other videos and it always matched. I think at the beginning I do like smoke tests with LiveCodeBench to basically see if it's passing the problems. It was passing them, so yeah, I don't go further, just didn't have time. So this video is already long, but if you want to run it, there will be a repository down below, Docker Compose file, you can run all tests, you can sync the file, and so on. And in last video, I have issues with audio, so this time I wish it's better because I get a new microphone. So if you like this video and you would like to hear more about this kind of stuff, then like and subscribe. I have also all the speculative decoding methods explained, some videos about explaining the quantization in detail and other stuff. So also let me know what you would like to see below and let me know which engine you actually run because I'm curious because I see more people using VLM SGLang because of the new features even on single concurrency and I use them for high concurrency so we could do some runs with them. So that would be it. Nice to see you guys and see you in the next one. Bye.